Assalamualaikum warahmatullahi wabarakatuh. We are from Group 6 and today we will be talking about how eigenvalues are used in real-world application, specifically in modeling population growth. It also one of the key tools used in the population matrix model or PMM. This model helps predict whether wildlife or plant population will grow or decline over time. They are based on vital rates like survival and fertility, which are organized by life stages. The dominant eigenvalue represented by lambda show the population long-term growth rate. If lambda is greater than 1, the population is expected to grow. If lambda is less than 1, it will decline. Eigenvalues also help managers decide which life stage to target for population control or conservation effort. Overall, this supports real-world decision in ecology, conservation, and wildlife management.
In this section, I will explain the mathematical method used in population matrix models, specifically how eigenvalues and eigenvectors are used to analyze the growth of populations. Let's start with the basics. In population ecology, we often divide animals into life stages like juveniles, early adults, and late adults. At each stage, animals either survive, move to the next stage, or reproduce. To model this mathematically, we use matrix A and a vector nt that represent the number of individuals in each stage at time. The formula is nt plus 1 equals to a and t. This means the population in the next year equals the matrix A times the current population. Matrix A contains all the survival and reproduction rates for each stage. Here is sample matrix A used in the deer study. Let me explain what this means. In row 1 consists of 0, 0.58 and 0.70. These are fertility values. Adult deer in stage 2 and stage 3 can produce young, which is juveniles. And row 2 consists of 0.14 and 0 and 0. 14% of juveniles grow into early adults. And lastly, row 3 consists of 0, 0.77 and 0.80. 77% of early adults survive and become late adult. 80% of late adults survive to stay in the same stage. This matrix captures the whole life cycle of female deer. Once we have matrix A, how do we use it to predict future population growth? So, we use a tool from linear algebra called eigenvalues. Eigenvalue tells us how the system behaves over time, especially the dominant eigenvalue, usually written as lambda. So this lambda tells us if lambda greater than 1, population is growing. If lambda equals to 1, population is stable. If lambda smaller than 1, population is shrinking. So to find this lambda, we solve the characteristic equation. The characteristic equation is the formula used to calculate lambda from matrix A. For a 3 by 3 matrix like ours, it looks like this. Lambda power of 3 plus p lambda power of 2 plus q lambda plus r equals to 0. The letters p, q and r are calculated using all the elements of matrix A. This is a bit technical, but here's a raw idea. P equals to negative sum of the diagonal elements of A, which is survival in the same stage. Q equals to products of pair of survival and transition elements, and R is more complex interaction, which is triple products. So when we solve this equation, we get 3 lambdas, which is eigenvalues, but we usually care about the largest one because it tells us the long-term growth. In the deer model, they calculated the characteristic equation and found lambda power of 3 minus 0.8 lambda power of 2 minus 0.081 lambda minus 0.0105 equals to 0. Then they test how changing some of the matrix value affect lambdas. They tried 3 strategies, which is firstly, increase survival of early adults A32 by 10%. The result is lambda increased by 1%. Second, increase survival of late adults A33 by 10%. The result is lambda increased by 7%. And lastly, when they increase both A32 and A33 by 10%, the result is lambda still only increased by 7%. So, even though they changed 2 things, the effect didn't double. Why? We will talk about this in the next slide. This happens because not all changes in matrix A affects lambda the same way. Some values are more sensitive than others. In this case, changing A33, which is late adult survival, has a stronger effect. Changing A32, which is early adult survival, has less effect. Also, when you change both, some effects cancel each other out in the equation. That's why managers need to understand the math before making decisions. It saves time and resources.
Now, let's move on to the interpretation and analysis of our result. In scenario 1, we increased the survival rate of early adult by 10%. This led to a slight increase of around 1% in the population growth rate, represented by the dominant eigenvalue lambda. This means early adult survival contribute positively but not significantly to overall population. In scenario 2, we increased the survival survival of late adult by 10%. Surprisingly, this caused lambda to decrease by about 7%. This suggests that too many long-living adults might slow down population growth, possibly due to resource competition or reduced space for younger generation. In scenario 3, both early and late adult survival were increased by 10%. The growth rate still increased by approximately 7%, but the positive impact from early adult was mostly cancelled out by the negative effect from late adult. This shows that changes in different age group can have opposing effect that don't always add up directly. In conclusion, our model show that different age classes impact population growth differently. Enhancing early adult survival must slightly boost growth, while increasing late adult survival could slow it down. This highlights the importance of focusing on specific life stage in conservation and wildlife management strategies.
To conclude, our project focused on modeling population growth using a system of differential equation, where eigenvalue help us analyze the long-term behavior of the population. We found that a positive eigenvalue means the population is likely to grow, while a negative or zero eigenvalue suggests it will decline or stabilize. This project shows us that mathematics, especially eigenvalue, can be applied to real-life problems and help in decision-making for things like city planning, healthcare, and resource management. We also improve our teamwork and problem-solving skill throughout the process. Although our model is simplified, it opens the door for future improvement, like using real population data or creating more complex models to reflect reality better. Overall, this experience made us appreciate how mathematics can be both practical and impactful in understanding our work.